Nomor matricol.
Yeah, I know the register number, but I don't have those.
Okay,
Yeah.
fair.
If you are going to send me your register numbers, I will put them there, I think, and then hide the name column. And yeah, you are going to be able to see the whole register file, I think. But I don't have your numbers. I don't even know how many of you are kind of registered for the class.
Well, in case this is wanted, we can just simply send the register numbers.
Yeah. If you want, you can send all of your register numbers by email. So do not, or you can write them in the chat. I think it can be good also. But yeah, I don't know. I think email would be better because I will have all of them. I will post some sort of an announcement in the Discord server. Okay, so we still have colleagues joining. We will delay a little bit. But you can ask your questions if you have. Okay, so first of all, is anybody here that still didn't send the homework? That's sort of.
I'm sending it right now.
Okay, good, because it was sort of an agreement that I'm not going to grade it after I start the lab. So if you have partial stuff, please. Please send them now. So. Okay, so I can see your register number is sort of an IBAN account. Oh my god. Good, let's go. Admit everybody, and I think we will start soon. I'll start sharing the screen. If you have questions, please let me know. So somebody just send me his Nomor matricular registration number. I don't know what's the official English name for that in your university on Discord. So you can send it to me as a private message and include your name so that I can match you. And after I will have this, I will update the file for you to see the whole register.
Do we all have to send the?
Well, I don't have them, so this is why I'm asking you to send it as a private message, because I don't want to mess it up.
a private message on Discord or an email?
Yeah. Okay, so you should be able to see my screen. I think somebody is still joining. Okay, I will let you know. So, if there's somebody that, I don't know, had some question, this is the right moment to ask. So no questions? Okay.
I have a question.
Okay, go ahead.
We're gonna use the same image for exercise 2 and 3, the checkerboard one.
Yeah.
Okay.
So I will show you what's the matter with that. I don't know if we are going to be friends after this lab, but it's going to be a lot of math today and also next week. So we're going to look through it, and yeah, it's sort of short, but I want to go into the details because I kind of observed that you don't have a lot of mathematical background. So some of you I can let's say derive from your homeworks that are sort of more okay with thinking in the mathematical way of doing stuff, but some of you don't. So I will simply go through this in detail. Yeah, so you can see. So first announcement for some of you that didn't got the points for the homework because they sent me the homework, let's say in the first days. All of you got full points. I just wanted to wait a little bit more to see how I'm going to grade the homework. So the idea is that if you don't have an email from me telling you that you have less than 4 points for the homework, everybody got full points. So 4 points for the students that sent me the homeworks like earlier. Everybody else, I think. I don't know, maybe we have some exceptions, already got the grade. I will check my email, and I see just Teofil that just sent his homework to me. I will grade it after the lab. So yeah, I think you are going to be the last one. Okay, good.
I have a question. For the link inside the notebook for the second laboratory, the first link with the 2D convolution, we need access to access that notebook.
Okay, I will update it, and you won't need anything else. But you still have the this sort of solution demo is the same, but I think the link used there is linking to another collab. That's the idea. So yeah, you all had the convolution. I told you this is how this correlation in fact works. So just sweeping an image with a filter here. So you can see my mouse pointer.
Yes.
Yes, we can.
Good. Because I'm not going to have any other solution for me to show some particular stuff. So just sweeping this image using these filter weights, Okay, we still have colleagues joining. Sorry. I hope everybody's in. No. So we are going to sweep the image, and we are going to element-wise multiply the values in the image with the filter weights, and we are going to sum this and get the result of the correlation. I already told you last week, this is a misuse in the field. Basically, what's happening is that we're using a correlation, not a convolution. So the term got misused, and we have convolutional neural networks, but they are not convolutions. I told you the generic operation is a convolution in a particular case where this filter weight matrix is symmetrical. So this is a correlation, in fact, in most of the cases. We already, I think this solution is easy to understand. So we are going to isolate here a patch, computing the displacement by half, the integer half of the filter weight size, and we're going to isolate a patch and then call the aggregate function on this. And the aggregate function can be either this one or this one. Because I wanted to show you the difference between using basic indexing operation on matrices and using NumPy. So some of you did this in the homework and observed the same behavior as I did. Maybe not exactly the same behavior because your machines are different. Up to some extent. This is the simple Sobel filter. I think the majority of you got used to this sharpening filter, and I applied it on the Blender image with the matrix sum and NumPy sum functions as aggregations. And here I just wrote a benchmark that's going to measure the execution time for the convolution with the different aggregate functions. And I got this sort of result with the red line. We have here the dummy matrix multiplication and summation. And here we have the NumPy sum on the element-wise block multiplication of the matrix with blue. Some of you in the homework, some of you discussed about the number of iterations that decreases with the increase of the filter size, and this is correct. So I gave full points for this answer for everybody, but there is another fact here that I think none of you pointed out, and somebody got some sort of let's say information in advance from me, because I asked him what the configuration of his cache memory is. So we have, as you can see, we have some sort of sharp points in some locations, and this can be explained by the cache configuration of the machine we are working on, because they are happening for NumPy sum function and also for the aggregate with the dummy summation. So this explains that, and this difference in the gap here can be explained by NumPy that's a high performance library compiled using, let's say, any sort of performance that can be extracted from your processor. Yeah. I don't know if you know about computer architecture, the cache, the current cache configurations on Intel processors. In some universities, this fact is studied. I think up until 2019, Intel provided enough information for some professors to write course material on that. So there are some resources on this, but I think everybody should know what AVX is. Is anybody here that doesn't know what AVX is? So you all know, good. Yeah, so basically it's just using your processor, yeah, the capability of your processor to do vectorized calculus by employing vectorized instructions, yeah. So you can use the parallelization given by AVX, at least up until Haswell, I think it was 4x. Yeah, after Haswell, I think they got even further, but there is nowhere near the necessary amount of information such that somebody can build a course material on that. So up until Haswell, that was I think the fourth generation. We had the information necessary, but we can just think about scaling the number of components in the processor, not including new instructions in the instruction set. Okay, if you have questions for this, please let me know. I told you that I'm going to also comment about the requirements from the homework. So basically what I'm going to ask from you is not big implementations also. I'm going to ask you to comment about some methods. Many of them are implemented, so you have to do just a follow-up on them. And I'm really I'm really interested in your comments about your results, yeah, because this is the only way for me to see how what you got from the implementation. So if you get a task to do something and you're doing it because everybody did it, I think up to 2 or 3 students, everybody got full points for this homework because I just graded the implementation and not the comments made about the results. Up to some extent, okay. You seem to be very good at implementing stuff, yeah, but you have not, let's say, the feeling of thinking about what you do, yeah. And I really want to see your opinion about the results, why something is happening, what's interesting about this. So just this part is going to be like a part for any task I'm going to give you to homework, yeah. Yeah, of course it's going to be difficult for me to grade it, and the biggest part of the grade is going to be the implementation, of course. But yeah, I have to get a feeling about what you think about what's happening there. Yeah, that's the whole idea. So be kind of be a little bit more generous with your comments if. Yeah, you're going to have homeworks for this lab as well. So I'm really curious about what you think. Okay. Any questions?
If we have, so the comments, do we need to write them in a separate file, or it doesn't really matter?
That's why that's why we're using Colab, I think. So Colab, yeah, you have two types of cells. You can see here. You have a type of cell with code and a type of cell with text. And in this text cell, you can write anything. You can insert images and so on, whatever you want. Yeah, links. That's it. So this is why I'm using Colab for now. Yeah, because you can comment and also you can just plot something, and yeah, there by observing the graph you're plotting, you can explain what's happening there. That's the advantage. Yeah, of course you can do it in Python as well. You can leave some comments there, but I have to yeah, as I told you, this behavior I observed at a lot of your graphs that you sent me if you plotted something, but for the majority of you it was a little bit different because the processor changed, of course, and the behavior depends on your processor and the amount of RAM you have and so on. If you are going to argue that your graph is like that because of something, and I'm going to rerun it on my computer, I can be in a situation that I would not agree with your comments. Yeah, I think it's logical. So this is the best way. Plot your results, comment about your results there, and that's it. Yeah, if you plot something and it doesn't look good, you can just replot it, delete the cell, so it's not sort of constricting or something like that. Okay, any other questions? I think we are going to go to the camera pipeline. So as you can see here, the camera is a pretty difficult model that consists of various steps. Yeah, we are beginning with the optics here. So I think some of you have DSLRs. I think the majority of you should have seen one of these cameras, so this shouldn't be something new for you. So we're beginning with the optics. Of course, the quality of the image depends on the quality of the optics you're using. So this is why we have the standard 1855 millimeter optic and another type of optics with different filters and different capabilities that cost a lot more. Yeah. So we're starting with the optics, and then we have some sort of analog to digital conversion. Yeah. Is anybody here that doesn't know what analog to digital conversion is? I think for engineers it's pretty obvious, but okay, so I think you all know. This is a type of filter that can be used as a sensor model for our cameras. So as you can see here, we have sensors that are sensible to blue light, green light, and red light. As you can see, we have more sensors that are sensible to the green light than we have for the red light. Is anybody here that wants to tell me why this is the design choice for a camera? I think you had this in the lecture. Yes, no, maybe? Is anybody still here?
Yes.
I'm gonna give points for answers, so I'm not expecting to to stay here waiting for an answer. So take your shot. So you don't want. So the design choice for more green sensible sensors is that the human eye is more sensible to the green light. Yeah, this is how simple this is. And this sensor needs to be read somehow. And here we have the ADC. That's analog to digital conversion. So basically, this sensor is going to give us, let's say, a current or a voltage, and this voltage is going to be measured, and the value on 12 bits is going to be passed further in the camera pipeline. Here we have something that's called the white balance. Do we have photographers here that know what the white balance is and the color balance is?
The white balance is the brightness of the white in the picture, something like that.
Yeah, it's adjusting the brightness such that the real white is going to be white in the image. Yeah. What's your name? Because I want to mark you for the bonus.
Giran Andrei.
Okay. Good. So we have the white balance. Yeah, we got here. Now we have the demosaicing, and we're going to see how demosaicing works. Next, we have denoising. Yeah, and then some color transforms, tone reproduction. Yeah, color transforms. You already saw in the lecture that there are a lot of ways to represent colors. Yeah, you have the RGB space, you have the ICBCR, you have the HSV. There is a lot of standards for this, and some camera models are using one standard or another depending on the application and so on. And next we have the compression. Here, you're most likely going to get the JPEG compression standard. Is anybody here that knows what JPEG uses for compression? Come on, you can Google it. Okay, JPEG uses the wavelet transform. I don't know if this is something new for you or not, but for the engineers, this is not something new because wavelet is used nowadays in a lot of standards and so on. But do you know the Lempel-Ziv algorithm? At least? I guess you don't. But imagine it as a wavelet transform and then using some sort of a Lempel-Ziv-like algorithm to compress. And you are going to have the RGB with 1 byte per channel. What's the main problem with this when we are going to have applications is that each of those steps, is non-linear, And when you have a combination of non-linear functions, as you can see, this is like a composition of functions, It's very difficult to establish a mathematical model for the real world, before the optics and the one that's going to be represented here in the RGB image. And we are going to discuss about this as follows. We have the Bayer filter, as I already told you here. This is an example of Bayer filter. And you can imagine, here, you can imagine that for each RGB pixel you have 3 values, The R, the G, and the blue, the B for the blue, in this Bayer filter, as you can already see, we have a lot more greens than blues and reds. And each pixel can be decomposed as a blue-green, green-red pair, and imagine the Bayer filtering having the value for the blue, the same value as you have in the image, So this is simply copied. When we have areas, so pixels that do not have a blue value, a blue cell in the Bayer filter in the local neighborhood, we are doing linear interpolation, basically, and blending the values in the Bayer filter in the neighborhood. But this is not going to happen in this exercise. So as you can see here, we have four cases. As I told you, for each RGB, we have blue, green, green, red, or blue, green 1, green 2, and R. Yeah, and we know that all the green 1 values in the Bayer filter start at even rows and odd columns. All the green 2 values in the Bayer filter are at odd rows and even columns. Yeah, you can see a cross between this, case A and case B. The blue values are going to be at odd rows and odd columns, case C, yeah, and case D, the red values are going to be at even rows and even columns, as you can see there. And now we have an exercise, yeah, that are going to, we have here a Bayer filter function that we can use to merge 3 channels for blue, green, and red, and return the BGR image. And we have the demosaicing function here that we are using an image to complete the corresponding Bayer filter. Yeah? So as you can see here, the corresponding Bayer filter is twice as large as the image. Yeah, because I told you already, we are using a neighborhood to compute the local value of a pixel, and this is the case here. And you can see here, yeah, we are using blue. We are starting at even columns, even rows, even columns, and we are putting there the blue channel in the RGB image. Yeah. Next, for the green, yeah, we are starting at odd rows, even columns, and we are putting there the green layer of our input image. And green 2, yeah, even rows, odd columns, and we are putting the same, yeah, as you can see here, it's the same image, the same channel in the input image I here. So you might think that in the camera, yeah, as we have here, is possible that a green 1 value is going to be different than a green 2 value, because this is the physical world. Yeah, the intersection of ray light, a light ray with the filter is a physical phenomenon, and we are not going to have this perfect alignment here, but we have a simulation here. So based on an image, we are going to compute the corresponding Bayer filter, and based on the Bayer filter, we are going to reconstruct the image that we started with. So we have here the render image. We are using the demosaicing function to compute the corresponding Bayer filter. Yeah, and then using the Bayer filter on the same on the Bayer image that we built here, we are reconstructing the same image. So as you can see, the Bayer filter is greenish, and yeah, maybe some of you who had also DSLRs or so at some point had access to the filter, the physical filter in the DSLR camera, and you can also observe that the filter is greenish, because this filter has more sensors that are sensible to the green light, as I already told you. Yeah, so this is demosaicing. It's just a matter of indexing. Yeah, and this structure for the Bayer filter is just a design choice. Yeah, we have more filters. You already saw it in the lecture. Rad already told you there are multiple technologies for the filters. Yeah, there are also in history, 99% analog cameras, 100% analog cameras, of course, because this is how this sort of photometry started with. So we have an optic system that concentrates light in an area, and we are using some light-sensitive substances on a piece of cardboard or wood or paper or so on to get a representation of the real world through this optic system. Yeah. So this is how the DSLR works. Yeah. And now we're going to see how we can establish some sort of correspondence between the represented space, the image representation, and the real world that has the object represented in the in this space. But for now, if you have questions, please let me know.
So why does the filter have a lot more green in the first place? Is it just an arbitrary choice, or is it something?
It's a design choice based on the fact that the human eye is more sensible to the green light than it is to the blue light or the red light. Yeah. So you had the lectures with Radu, and you saw some graphs for the RGB space, the ICBCR space, yeah, and you can see there that graphs and the shapes that are the borders of those representation spaces are designed, yeah, such that the representation is going to be as meaningful as possible to the human eye, yeah. So if you're going to look at RGB space, color space, we are going to see an image here. Yeah, you can see here that in this representation, the area that's so we have the sRGB, the Adobe RGB 98, and the Photo RGB. If you're going to have some cameras, you're going to try and match some. You are going to have some problems, yeah, because different standards tried to represent this space using different representation, yeah, and each representation is just a design choice that's done such that the space is going to be as useful as possible in some application. For the RGB, we are trying to represent something that's as closely as possible to the way we perceive the reality through the human eye. Yeah. With some other spaces, we may want to go beyond the human eye possibility to gain some advantage here. Yeah. Maybe you want to go to something that's closer to the infrared or the ultraviolet, depending on the application, of course. We have thermal cameras for that. For the infrared light, we have thermal cameras that are using a representation that's designed around that principle only. Yeah. So this representation is just a design choice, yeah, made such that the representation of the color is as close as possible to the way we perceive the object represented in that image. Yeah. So we try to code the limitations of the human eye in a representation space. That's what's happening here. And after doing so, we needed a filter for this transformation between the perceived light after the optics concentrated there and the final image. Yeah? And this is just a design choice. Yeah, it's not something that came as I say a mathematical derivation, and this is the optimum. There is no optimum here, but this is the as close as possible and as cheap as possible, such that the price of the cameras can go lower. Yeah.
I see.
Because, yeah.
Thank you for the explanation.
Good. Any other questions? So we don't have. I think we are going to go ahead. So now we are going to try and match some image points to some real value objects. Yeah. And we have here with capital letters. Yeah. We have a set of input points that represent corners of this checkerboard pattern. Now, as you can see here, we have 27 millimeters here. We have 0.027 meters. We try to stay in the international system with our measures. And as you can see here, the origin of the real world coordinate system that we are considering is with the center aligned with this ridge of the calibration pattern that's folded around. So you know that here you are 27 millimeters off the center on the x-axis. Here you are 54 and so on. So this is why what these points represent. So represent corners around the origin of this system. And we have here with non-capital letters, we have points on the image. So basically here in the image, this is the 000 point, that's the first. And this is the 866 pixels. So judging by the line, this is the 866, and judging by the elevation, we are at 1132. Yeah, you may wonder why we use the real numbers for pixel values, because the location of the pixel is an integer. If you are going to use some sort of a library to give you the position of the mouse pointer in one image, you are going to get a real number as a result. So basically, this is sort of a result of using MATLAB for getting the position of the mouse pointer in the image frame that's going to appear when you plot the image in MATLAB. Yeah. But if you're going to say that we should have used integer numbers, I will agree with you. Yeah. So basically we have here the same number of points, and now we plot this point. So as I told you, this represents the origin, and then we go 27 millimeters far on each axis, and log the pixel that's corresponding to that real world point. So we are going to use these points to derive a mathematical model for the reality. Yeah, and I think some of you should already feel what is the problem with using mouse clicks to get positions throughout the image. Of course, this method is going to be very noisy, and is going to depend on the DPI you have on your mouse. Basically, the DPI is a measure of how smooth the movement of your mouse pointer is going to be throughout this image. And if the DPI is high, you're going to be very you're going to have the possibility to be very careful with what you choose, but you are going to have lower DPI because higher DPI means the mouse is expensive. You cannot select the exact position representing a pixel unless you have a very large zoom. And also, by zooming, you have to create a mathematical model such that you can link the position of your mouse in the zoomed image to the position of the mouse in the original image. So we're going to stick with this, and we're going to see what the results are, and then we're going to comment on this. But keep in mind, this method of picking positions in the image is very nice. But for the image, you cannot know exactly what pixel represents the intersection between the lines around a checker in the checkerboard pattern. So we have noisy data, and our algorithm is going to use SVD, and this is going to be a problem because, as you should know already, SVD is very sensible to noise. And because of this, we have to normalize the data such that we can minimize the influence of the noise in our model. And this is done as a data normalization step, as I described here. Firstly, we're going to center the data around the origin, so basically subtract the mean. With mu, here I noted the mean. You can see we have non-capital letters and capital letters as a convention. The capital letters are 3D real-world coordinate system points, and non-capital letters are 2D image representation points. Everybody should be okay with that until here, I guess. So here is what's happening. We're going through our array that represents the point, and we are subtracting the mean out of each point there, such that the values are going to be centered around the origin. Next, we are going to compute these values. So we have the lambda values that are going to be the inverted sum. So think about this as a vectorial equation. So basically, this equation is going to be two equations for the x coordinate and for the y coordinate, and this equation is going to be three separate equations for x, y, and z. So we are going to need to compute the inverted sum of these points and to divide to multiply this inverted sum by the number of points we have in the set. And this is going to be the square, and we have the square root as well, vectorial equations here. So think about this as this is going to represent two equations, this is going to represent three equations. And here we are doing exactly that. We are using the reciprocal function to simulate the vectorial nature of the equation. And here we have numpy.sum with the axis 1. This is going to return a vector, even if we have the sum operator. If you are going to specify an axis, we are going to specify the axis on which the summation is going to happen. And if we did so, with axis 1, the summation is going to happen on the columns. So imagine these points getting summed. So here we are going to compute the lambda values. Next, with these lambda values, we are going to compute the T and U matrix. So these are transformation matrix, such that our data is going to be centered around the origin, so it's going to have zero mean, and the variance on each component is going to be 1, exactly 1, yeah? And I asked you as a homework, I think is the last task, yeah, of this is to try and do a pen and paper exercise such that this behavior is going to be seen. So if you wanna go ahead with the math, yeah, feel free to do it. You are going to get a bonus point for that. So we're going to create these two matrices, and you can also see here we are going from the 2D world to the homogeneous 2D that has 3 components, and the 3D world to the homogeneous 3D that has 4 components. Yeah, and this is why this matrix is going to be 3 by 3, and this is going to be 4 by 4. Yeah, everything clear until now? Yeah, I think should be. And this is how it's happening. Yeah, we're going to build the T and U matrices. T is going to be 3 by 3, U is going to be 4 by 4. And we are going to fill these values by the lambda values. I think, okay. Anybody still here?
Yes.
Yes, we're still here.
Yes.
Good. Good. Yeah, I hope you can keep with me. So this is where
I'm sorry. I'm not sure, but you are still interrupting. I'm not sure if it's from my connection or yours.
I don't know.
Anybody confirm that?
I've also heard him interrupting, but now he is heard fine.
Okay.
Okay.
So just to know, sometimes we might not heard.
Okay. If there is a problem, just interrupt me and I will go over again. Yeah.
Okay.
On that line. So.
Yeah, it's not very often, so it's okay.
Well, you know how the internet is in Germany, so
Okay.
yeah, it's not like in Romania. It's far away. Okay, so we have here the homogenization of our input points. This is like easy. We're going to create a 3 lines n columns matrix, and we're going to put there the values that we have there, and the last line is going to be filled with 1s. For this capital letter, yeah, it's the 3D world. We have 4 lines. The last line is going to be by 1s, and the first 3 lines are going to be our input coordinates. And then we're going to apply at the left our transformation matrices to get the normalized way. So, okay, so next we have this sort of monster. It's known as a block operation for the matrix, and I will quickly tell you how this is derived. Yeah, so we have the equation, yeah, that the image world coordinates are exactly the 3D world coordinates that are projected, yeah, to a projection matrix P. Yeah, and we know that the 3D world is 4 by 1. Yeah, you know that the image world is 3 by 1 in homogeneous coordinates. Yeah, so the projection matrix is going to be 3 by 4. Yeah, I think we should be okay with that. So 3 by 4, this means that we need to compute 12 unknowns such that we can get a mathematical model for the projection matrix P. Yeah, these 12 values can be a solution of a linear equation, yeah, with a matrix having 12 rows and 12 columns, yeah. So as you can see here, yeah, we have 4 values here because we have capital X that's normalized. So 4 values here, 4 values here, and 4 values here. We have 12 columns in our matrix, and we have 2 lines, yeah. Each row is a line in our block AI, yeah. And this block AI gives us 2 equations, yeah. It's okay with that? Here, X and Y, yeah, it's just the X and Y coordinate in the camera image representation system, yeah. So think about this one as a scalar, yeah. And this scalar is going to be multiplied with the whole point xi in our coordinate. This wi, yeah, means that we can get our projection matrix up to a scaling factor, yeah. So we are not going to have a unique solution for this algorithm, yeah, of deriving the projection matrix, and this algorithm is limited by getting the projection matrix up to some scalar. For now, we are going to consider all these scalars equal to 1, yeah. So we have here with a single point correspondence between this xi and the point in the image coordinate that's represented through the x and y value, we are going to get 2 equations, yeah? And we need 12 equations to derive the values of our matrix P, yeah? So we are going to need at least 6 of these blocks. So we are going to need at least 6 of these blocks to get a full matrix such that we can solve this linear system. Why this linear system? This is another important fact. We have this equation here that x in the camera coordinate system is equal to an x in the 3D world, homogenized, of course, that's going to be projected to the projection matrix P. Yeah. If you are going to take this equation and we have points for x non-capital in the image coordinate system, we have points for x in the 3D world. Yeah. And if we are going to write this equation and group the linear terms after the values of the P matrix, we are going to see that we can have a column vector, yeah, with the lines of the P matrix. So basically, imagine P1 by 1, P1 by 2, P1 by 3, P1 by 4, and so on. Yeah, that's going to be stacked vertically. This is why this transpose is here. So imagine just a flattened version of the matrix P, yeah, in one column vector, and we have this system of equations. So basically, this block, the structure of this block, comes after writing the correspondence between 2 points, 2 sets of points, yeah, and writing this equation and then grouping the linear terms with the unknowns, the values in the projection matrix P. Is anybody here that didn't got this? I think we are okay. So as you can see here, yeah, I got a matrix named A that's 12 by 12, and the block, that's the temporary, that's 2 by 12. And in this block, I'm going to put these values in this format. Yeah. So here, 0 by 4, 8 by 12, 4 to 8, 8 to 12. Yeah. 4 to 8, 8 to 12. 0, 4, 8 to 12. Yeah. And I have implemented exactly the completion of this block. And then I'm going to put everything in this matrix A here. Next, we are going to use SVD to solve this linear system of equations. Is somebody here that doesn't understand why we use the SVD? You know what SVD is?
Not really.
Okay, SVD comes from the singular value decomposition. I will make some comments here. So the SVD algorithm is a nice tool in the numerical methods sort of lecture. I think you should have a numerical calculus or numerical methods, and you can imagine the SVD that you are going to get three matrices, yeah, and you are going to get the matrix U, the matrix sigma, and the matrix V. Yeah? That's the SVD decomposition of a matrix A. Yeah, and this is done in such a way that U multiplied matrix multiplication, yeah, with sigma matrix multiplication multiplied by V transposed, so I'm going to put a T here, is equal to the matrix A. Yeah. So the algorithm is set in such a way that these U and V matrices are going to be orthogonal. Yeah. And on the sigma matrix, you can imagine it as a diagonal matrix. So think about it as the identity matrix, but with different values on the diagonal. And these values are known as the singular values of the matrix A. Yeah. If there is a possibility here, if the matrix A is equal to the matrix A transposed, yeah, you know that these singular values can be linked to the eigenvalues of the matrix A. And linked, yeah? Basically, you're going to see if you are going to compute, like an example, you have the SVD of A multiplied by its transpose. Yeah? You're going to see that the singular values are squares of eigenvalues. You can see why here. So basically you are multiplying a matrix with its transpose. Yeah, these singular values are going to be the square of the eigenvalues of the matrix A. Yeah, I think this shouldn't be so difficult for you to understand. So basically think about SVD as a way to find a set of orthogonal matrices U and V that are going to do the decomposition of the matrix A as this: U multiplied by sigma multiplied by V transpose. On U matrix, you are going to have the left eigenvectors of the matrix A, and on the V, you are going to have the right eigenvectors of the matrix A. On the sigma matrix, you are going to have the singular values, and the algorithm is built in such a way that the singular values are going to be on the diagonal and in the descending order. So basically, you are going to have the biggest singular value as the first one in the 0, corner, top left. If you're going to imagine this. Okay, so this is SVD. And I stated here the equation for the eigenvector. So you know that V is an eigenvector of the matrix A if and only if there exists such a lambda, such that A multiplied by V is equal to lambda multiplied by V, Is it clear? Eigenvalues, you should know from the algebra course. Okay, so what this means? So here we have a transformation, that's going to be applied on the vector V, a linear transform. You know what a linear transform is from the algebra course. You should know, I think. But think about it as any linear transform can be represented by a matrix, And if you're going to apply this linear transform on the matrix V, in the output space, this V is going to stay the same, and is going to be scaled by the lambda. We know that if lambda tends to 0, this lambda times V tends to 0 as well, because lambda is a scalar. This means, that the AV products tends to 0, to 0 vector. And this is what we have to compute here. We have to compute a vector V such that this matrix multiplied at the left of this vector gives a all 0 vector, We know, that the sigma values are going to be descending in descending order. So we know that the best solution for this is going to be exactly the last column, the last column of the matrix V. You understand why? It's exactly like this. If lambda tends to 0, lambda times V tends to 0, this means that A multiplied by V tends to 0. If we are going to get the eigenvector that corresponds to the smallest eigenvalue, we have the best approximation of our solution. Even if the eigenvalue is not going to be exactly 0, we have something that should be as close as possible to 0, Is right? Do you have comments on this?
Yeah, it's clear.
Okay, good. So basically, this is what we did here. We have the normalized P matrix as a 3x4 matrix, and then we are going to compute to get the lines of this matrix, as the last column of the V transpose. Why is the V transpose? Is because the algorithm SVD in Python works in such a way that is going to return you the transposed version of the V matrix. So you know from the documentation that the V matrix here is the transposed version, so you are going to transpose it again, just like this. And this is how we get the PN matrix. That's the projection matrix, that we computed for the normalized coordinates, So we did the normalization first, and we computed the projection matrix between the normalized space. Now we are going to apply the inverse transformation over the normalized matrix to get the projection matrix in the real world. Is it okay? So we applied the transformations on the input data. Now we have to apply them inverse to get the transformation in the real space. So everything here is linear. No, other than this SVD. Theoretically, if we have a solution for this, a unique solution for this system, everything is linear until here. So we can apply transformations on the result, the inverse transformations applied on the data on the result. So we are going to get our matrix P. And this is our projection matrix. To see that we computed the valid projection matrix, we started with a set of red points, yeah, you can see here. And above these red points, we plotted the projected positions in the image for the points we had in the real world, yeah. For these points, we computed the projections in the input image to match with the ones picked by us with the mouse. So until now, everything is okay. I should give you a break. And then we are going to decompose this matrix. If you have questions, now it's your turn. It's going to be break until 20 past.
So the dark blue points are projected on the two walls now?
So yeah. So basically what we did here, you can see with blue, yeah, we plotted the computed values. And the computed values, yeah, you can see here, is the homogenized, yeah, you have to divide by the last line.
Mm-hmm.
The homogenized variant of this, and this is the result of applying this projection matrix, yeah, at the left side of these homogeneous coordinates x, y, z that are not normalized, yeah. These are unnormalized x, y, z in the homogeneous space, such that it's going to be 4 by 1, yeah. And we plotted this to see how good our projection matrix is.
Okay, thank you for the answer.
No problem. It's very interesting to see that we already have a model between the real world and the image. Yeah. So basically, now, if we know something about the space we had when having the picture done, when shooting the photo, we can reason about what's in the image. Yeah. So we are trying to get a model between the real world and this image world. And this is like a visual test for our algorithm. Any other questions? Okay, so I'm going to get the list with the people that are in the meeting. So if everybody is going to join again or something, let me know. Yeah. We're going to start the last part. Is there anybody that has a question for now? Okay, we're good. Is anybody here that's not, I don't know, okay with this block matrix notation?
The block matrix just means like submatrices, right?
Yeah.
Ah.
Basically, we know that this P matrix, is a product of the intrinsic camera parameters matrix, and you had it in the lecture, multiplied with a rotation matrix, because the position of the camera in the real world can be described by a rotation matrix, because if you're going to rotate the camera, you can represent that rotation as a rotation of the whole space that you're representing. And you have a translation, because the position of the camera in the real world, you don't know it, and you have to build your mathematical model in a way that represents also that translation. So we have here a camera, intrinsic camera, a rotation, and a translation. If you want, to get this rotation and this intrinsic camera, you have to work with the 3x3 block of your P matrix, and we are doing exactly this. And we have another decomposition that's loved by all the numerical methods guys around the world, is the QR decomposition. Basically is a decomposition that means you have a matrix A, R applied to the matrix A, builds two matrices Q and R, such that A is equal to Q multiplied by R transpose. And because of the algorithm, these Q and R are orthogonal, of course, because let's say is in the mathematical definition of the QR algorithm, the method builds two orthogonal matrices. It's just a choice of the method. It's not like some sort of property of the matrix A that it admits, every matrix A admits two orthogonal matrices. Good. So we know that we can do this. Of course, people observe that it's numerically more stable to do it on the inverse of this block than to do it exactly on the 3x3 block, representing the products between K and R. And we know that R in the QR is a rotation matrix, and Q is an upper triangular. Of course, this is the choice of the method. So we know the definition of the intrinsic camera matrix, and we know that this is upper triangular. And we can guess that this inverse of the rotation is going to be the Q matrix in the decomposition, and the inverse of the intrinsic camera parameters is going to be the R matrix in the decomposition. So we know that for now. We're going to compute this R and K inverse, and then we're going to invert them, simply like that. So think about this as a numerically stable method, QR, where these matrices admit inverse. So we are not going to have problems with the matrix that have determined 0. Yeah. And we know that the last element, yeah, k2 by 2 is going to be 1. Yeah. So we're going to divide by the value k2 by 2. Now we should also know that the determinant of the matrix R, yeah, should be 1 as a rotation matrix. Yeah. Do you know what a rotation matrix in 2D is? Sort of all-around task in the baccalaureate. So you might remember this sort of exercises where you should know that applying 2 rotations is going to give a rotation with the rotation with added arguments. So I'm pretty sure you had this sort of exercise for the math baccalaureate stuff, because I remember I had a lot of those as well. And if you're going to compute the determinant on these, you're going to see that cos squared plus sine squared is going to be 1. Yeah. So we know that the sign of the determinant should be positive. Yeah. Because this method is okay up to the sine function, we are going to build the NM matrix, the normalization matrix, and this has to have the property that the square of the NM matrix is going to be the identity matrix. Yeah, and this QR decomposition can be seen, yeah, as using this normalization matrix, such that we can force the determinant of the R matrix to be positive. Yeah. And the definition of this normalization matrix is the diagonal matrix that has on each element on the diagonal the sign of the elements on the diagonal matrix of the Q here in the QR decomposition. Is it okay until here? So by forcing this, we can multiply this normalization at the right of Q and at the left of R. Yeah, and this is going to force the determinant to flip the sign if needed. Yeah. If the sign is going to be 1, the result is going to be the same. If the sign is going to be -1, this matrix is going to multiply to flip the sign of the determinant. So this is exactly what we're doing here. We are multiplying this normalization matrix at the left of the Q matrix in our QR decomposition, and this normalization matrix at the right of the R matrix in our QR decomposition. Of course, the QR decomposition, the Q matrix is R inverse, and intrinsic parameters matrix is going to be the R matrix. Yeah. And here I think it's not transposed, it's exactly Q and R. So I'm computing here the adjustment matrix, exactly, yeah, as the sign for the K, and I'm multiplying, yeah, at the right and at the left here. And now we're printing them. Now we know that the camera center is the point C that satisfies the equation that the projection of this point through the P matrix gives exactly the coordinates of the camera center 0, 0, the origin of the camera coordinate system. So again, we are doing again SVD on the P matrix, get the rightmost eigenvector on the same derivation as here, yeah, take the rightmost because it has the lowest sigma value, and the lowest sigma value means that it's the closest approximation of the solution. Yeah. Now we are going to homogenize it, the camera center, because it needs to be in homogenized coordinates, and we're going to print it as this vector here. Yeah, and the translation that represents what the position of our camera is in the real world. We're going to take the matrix R and we're going to apply it on the camera center. Yeah, and here we're going to have it. Here you have the massive book of Zisserman and Hartley. Public, you're going to have their workshop that they had on CVPR 99. And here in imaging geometry, you're going to have a representation, and now we have the camera calibration, so on, exactly like this. You can see, so basically here we have the equation that we used. Here we have the projection matrix as a product between K and R. K is the intrinsic camera parameters, R is the rotation matrix padded with a translation. Yeah. Or by moving this R matrix outside, we have the product K and R, we have the identity because R is orthogonal, yeah. And here we have the translation as R transpose times this translation, and the camera is the minus R transposed multiplied with T, the translation, yeah. So we did exactly that until here. If you are going to go further and further, yeah, you have also this derivation that is giving you the expression of the block. Yeah, we were discussing about in the last hour. So yeah, if you want to do a screenshot, if you want to search it on Google, it's public. You can work and you can get it and see what's happening. Another interesting geometry, projective geometry. We have two view geometries and so on. Epipolar geometry we are going to discuss about as follows and so on. So until here, yeah, we have everything said about the camera calibration. Yeah, you have to note that, of course, our initial equation we started with is that lambda, yeah, there is a scalar lambda that's equal to the depth divided by the focal length on that dimension, multiplied with xy, and this f we set it to our focal length, yeah, gives us exactly the z, the point in our 3D coordinates. So basically, if you're going to take this lambda and set it with z divided by focal length, and we are going to multiply it, is just this equation is used just to copy the depth coordinate, because by doing a projection of 3D into D, you are going to lose exactly the depth. So for this equation to be correct, this model to be correct, you have to add an additional equation to copy the depth here. Okay, yeah, I let you hear some interesting links for your, I don't know if you want to read. And because I put a task with simulating distortion in images, I'm just putting here a very short example of distorted image using a sine function. Yeah. So you can see here we have an image, and we want to have like 1.5 periods, and we're dividing everything by 3. Then we are going to compute the W, yeah, the frequency by using the width, yeah, the width, because we want a period and a half in our image. So in this image, shape is going to be something like height, width, and 3. There's going to be 3 channels for RGB. Yep. And we're going to use a lambda function here to compute the value for this sine function. X, yeah, is going to be our unknown here. And if you're going to apply the roll function over the image I with the shift, let's compute it here. So basically this shift gives us how the distortion happens. So basically distorted means the model, the model between the 3D world and the 2D world is distorted by this sine function, and by distorting the model, you're going to have an effect with each pixel, what this pixel represents in the human world. Yeah, it should have been here, but because of the distortion, it has a vertical displacement, and this is represented here. Yeah, so basically the distortion is simulated, applied on exactly the geometrical model, such that this is going to have a vertical transition done by the roll function here. And this is how we simulate distortion. A very easy task in the homework. I'm asking you to use a package from Python to simulate different types of distortion and to discuss about the results. And I'm giving you here an example. That's the barrel distortion. Yeah, as you can see in the, let's say, idealistic world, we would have something like this that keeps the scale of the represented Euclidean space in the real world. Yeah, so basically this scale is going to be kept, the scale mechanism, not the scale value, because we have a scalar there. Yeah, but we know that up to a scalar value, we can retrieve the position in the real world. But because of the barrel distortion that happens because of the chip lens systems, yeah, we will have something like this, yeah, where the scale in the represented space as lines of magnitude, yeah, is affected in the region closer to the corners of the image. And if you are going to go to epipolar geometry, you are going to see that we deployed some tool to remove this sort of distortion, to get an exact model between the two view cameras. Yeah. So this is the first task, just to read the documentation of this and simulate some types of distortion that you want, and yeah, just discuss about the results. So yeah, for the barrel distortion, I put here the answer because it's quite important and you are going to find it. Because of course nowadays a lot of the pictures are done with mobile phones that don't have a lot of space for very, very good lens systems. Yeah. So it's just a matter of design here for the mobile phone camera. Because if you're going to compare even at least now it's launched the S22 Ultra. That's, I think it has for now the best available camera from the, let's say, flagship phones. If you're going to compare the S22 Ultra with a DSLR camera of 24 megapixel, you're going to see that there is a huge difference between the capabilities of the S22 with all the AI built in and the DSLR. Yeah. So expensive and big optics really help in terms of photo reconstruction and so on. So this is the first task. Just deploy functions from the want package. Next, I'm asking you to try and play around with the OpenCV camera calibration tool. So just use the documentation, run a piece of code from there, and try to see the difference and so on. Next, I'm asking you to run the decomposition and so on. So the direct linear transform is the method of finding the P matrix. Yeah. Experiment with another set of points. So basically, I'm asking you to take the image and pick another set of at least 6 points that are corresponding to the real world, and use the direct linear transform with those points. Yeah. And the second part of the task, is to project all the square corners. Yeah. So basically, I'm asking you to iterate with x from 0 to some value that you are going to compute by adding 27 millimeters for each square. So just iterate through this domain and plot all the corners in the image. Yeah, it's not difficult. It's pretty easy to do. And the last one, I told you, if you want to do a pen and paper, you can either compute the mean and variance for the normalized data to see what's happening there, yeah. Or if you want to do a pen and paper exercise, follow the derivation here to see how this block comes up, yeah. So yeah, I'm going to update it and yeah, just pick whatever is I think easiest for you. Okay, then, if you have questions. No questions? Fine. Okay, I promised I'm going to tell you the maximum number of points achieved until now. It's 5.5. So 4 points for the homework, 1 point for attending to previous lab, and a half of point for answering to my questions during the lab. Okay, any other questions? Okay, I guess we don't have. We will finish 5 minutes early. If you don't have any questions, you are free to leave the meeting.
Goodbye.
Goodbye.
Bye.
Bye.
Okay,
Bye.
another question. Hey, if there is anybody that joined later, you have to let me know so that I can update the list. But I don't know if it's the case or not. So
Well,
why-
I was like 5 minutes later. That counts?
no. I did the list during the break between the 2 hours. So
All right. Okay.
Okay. I think everybody should be here.
Good. Goodbye.
Bye.
Bye bye.
Bye.
Goodbye.
Bye. See you next one.
Goodbye.